But I begin. Oh? No? No. So last time, if you remember, or if you don't remember, last time we discussed classical, simple Lie, complex Lie algebras. And I had no time to finish. One of them was not properly discussed. And this is the Lie algebra of symplectic Lie algebra, SP. Do you have any idea what it is and why it exists? Or maybe more general question, do you have any idea of the symplectic geometry? No one of you, or you have some idea?
My question is, how did they find it so long ago? Because it's from the very beginning, and I'm like, I thought
it is not precisely long ago, but you know, classical mechanics. It was invented some time ago, and this is actually the same as symplectic geometry. So symplectic geometry, I don't remember who said this, is refreshingly different from the Euclidean geometry. Mostly because, so we have, again we have inner product. But this inner product is not symmetric, it's too symmetric. So in particular, every vector you can imagine is orthogonal to itself. Has zero inner product with itself. Still, this geometry really is very interesting, sort of same as Euclidean geometry. There are isotropic planes. This geometry is even dimensional actually, but so dimension 2n of the space, and there are planes of dimension n which are isotropic in the sense that for every two vectors in this plane, its inner product is zero. Such planes are called Lagrangian planes, and this, Bob, is a sort of part of the answer to your question. Lagrangian planes. Certainly Lagrange himself didn't know that they are Lagrangian planes, but he knew pretty well what Lagrangian plane is. Yes, Lagrange, you know, this is more than 200 years ago. So the Lie algebra. Nothing dramatic about this Lie algebra. Simply we have Euclidean space. We have of even dimension. We have a non-degenerate skew-symmetric bilinear form. It is so important that the space is even dimensional. This is because in odd dimensional spaces there are no non-degenerate skew-symmetric forms, bilinear forms. You may know that every skew-symmetric matrix of odd order has zero determinant. And then we consider linear transformations, which, if we consider linear transformations preserve this form, it is a Lie group. The corresponding Lie algebra, we consider linear transformations which we consider which vector field which annihilate this form. The linear form itself, it is unique up to basis change, but still we need to fix it. So the form, I don't need even to write it because I need this form. I will need the algebra. But the form is, there are n basic vectors, E1, En, F1, Fn, and E's are orthogonal to each other, F's are orthogonal to each other, and Ei, the inner product of Ei and Fj is delta Ij. The Lie algebra The notation, sometimes people write SPN, sometimes SP2N. I don't know which is better. I write 2N simply to underline the dimension of the space. Consists of 2N cross 2N matrices. The matrix here is A. Matrix here is the same A transposed. B and C here, but this both these matrices are symmetric. It is not hard to check, and you can do it, that commutator of two such matrices also have the same properties. So this is a Lie algebra. It's a simple, I mean complex, everything is complex. So it is a complex Lie algebra, and the Cartan subalgebra is again very easy to check that this is a Cartan subalgebra. Diagonal matrices here, equal diagonal matrices with the diagonal entries lambda 1, lambda n, and zeros here and here. It has dimension n. R could be better. And then the roots are linear form on this, and they are plus minus lambda I, lambda j, but we do not exclude the case when I is equal to j. So 2 lambda I is also a root. By the way, I didn't say that the dimension of this Lie algebra is the same dimension as SO 10 plus 1. Very easy to check. Now, simple positive roots. It is obvious, so I write lambda I minus lambda j with I less than j, and lambda I plus lambda j for arbitrary I and j, they may be equal. I can write I less than or equal to j. And the simple positive roots are lambda 1 lambda minus lambda 2, lambda n minus 1 minus lambda n, and also 2 lambda n. I do not check. This also, the check is not especially difficult. I sort of skip it, and you see this 2 lambda n. This 2 lambda n shows that the inner product of this and this is not negative 1 as it used to be, but rather negative 2. Which, actually this root is longer than this. The length of this is 4, well, 2 squared, and the length of this is 2. And by this reason, the Dynkin diagram is the same, but now this vector is longer, so we write it like this. So the difference between Dynkin diagrams, it is called CR if R is the number of dots, CN if you use my previous notations. So the difference between the Dynkin diagrams of BR and CR only in this. In particular, if R is 2, then B2 and C2 are the same. This is the reason why we had only one such system of roots, dimension 10, in the plane. B3 and C3 are very much different. And again, if you had time to look into my pictures, the geometric appearance of the system of roots are different. What is the same for these Lie algebras, besides the dimension, which certainly is the same? I mean BR and CR. So SO to R plus 1 and SP to R, depending on your notations. The while group is the same. it is again more or less clear. The symmetry group is the same, although the roots themselves are sort of different. Now what else? I mentioned that there is such a coincidence. Well, let me say something different now. And this is the following. Yes, I wanted to mention that if you consider all classical Lie algebras, and the Lie algebras of the types A, B, C, and D are called classical, then there are isomorphisms which I want to write. SO3 is SL2 and also SP2. I use this addition too. And then SO4 is the same as SL2 plus SL2. SO5 is the same as SP4, and SO6 is the same as SL4. I want to say that actually in all the cases the Dynkin diagrams are the same. Let me begin with SO2n. So SO2n is the n. It looks like this. N SO is equal to n. To R is dr. R is the number of dots here. If R is 4, then it looks very nice. 1, 2, 3, 4. But if R is less than 4, then this should be SO6, and this without even this is SO4. So this sort of something additional to these two dots, which gives you this and this isomorphisms. This we already discussed. It is B2 and C2. This again is very clear, but all these Lie algebras have rank 1. So actually we don't need to say anything at all. Just one dot without anything. Now, let me say just several words about the exceptional Lie algebras. There are 4 of them. G2, F4, E6, E7, and E8. We actually have, maybe not very explicit, but still some description of the root systems, because we have classification of all root systems. The Lie algebras themselves are not immediately clear how to define them, because you need to know some cryptic numbers n alpha beta, and this should satisfy some equations. And this is a sort of complicated system of equations. The more so that the number of roots is quite big for these algebras. I will mention the dimensions. Dimensions are 14, 52, 78, 133, and 248 for these 4 algebras. Some of them have descriptions. E8 was the description of E8 was the latest of all descriptions. G2 can be described if you know this language as a Lie algebra of derivations of the algebra of octonions. Have you ever heard of octonions? Good. Octonion not associative, still we can consider derivations. Derivations do not triple products not required when we consider derivations. So it is very natural to consider, and this is Lie algebra derivations. This is G2. It has dimension 14. All the rest, well, they arise in physics as Lie algebras of infinitesimal symmetries of different systems. The 8 is very popular in topology. This, as a, topological dropout, I can confirm that the 8 is one of the favorite objects in topology. Yes?
Can you say just a little bit why it's important?
You know, if I say why, I must apologize. No, it's not precisely true. This diagram is very important. This diagram is very important, and this can be used if you construct manifolds. So imagine that you have a manifold, well, even an algebraic manifold, but in topology it is sort of better. Say 8-dimensional manifold, and in the middle dimension we have 4-dimensional cycles, they are spheres, and these edges show the so the self-intersection of every sphere is 2, and the intersection of between different spheres is 1 or 0, as shown by this diagram. So there arises such a manifold. This is used in many constructions, in particular in constructions of exotic spheres, and so on. But not only this. 8 is popular in K-theory. So if you don't have anything else to ask, I erase this and we forget about it. My next subject. Real Lie algebras. The real case. Certainly, a complex case is very convenient because the field is algebraically closed if we don't know. But from the point of view of geometry, certainly a real case is something which you need to consider. Who cares of orthogonal matrices, complex orthogonal matrices? Real orthogonal matrices, yes, it is a compact Lie group. So the mere notion of compactness, when we consider Lie groups, certainly arises when we consider real Lie groups and not complex Lie groups, which are never compact. Good. I begin with compactness. So there are real Lie algebras. They may be semi-simple, simple, whatever. The theory of semi-simple Lie algebras, killing form, everything, can be applied to the real case. It is sort of clear. Now we consider a real Lie algebra. Again, it has killing form. Which we define using the adjoint representation, or actually if this algebra is simple, any other representation. Now definition. May seem stupid. G is called compact if the killing form is negative definite. You can ask why not positive definite, and I answer because this form is never positive definite. Positive definite would be okay, would have been okay, but it never happens. So why this strange terminology? First of all, negative definite in particular means non-degenerate. So a compact, we can say only real algebra. I will not even repeat this. A compact Lie algebra is, first of all, semi-simple. The Cartan criterion is valid for real Lie algebras as well as for complex algebra. Now, what is the relation to compactness, which is a topological notion? If G, so there are the following statements. First, if G is a compact Lie group, then the Lie algebra G of this group is non-positive. If additionally G is semi-simple, well, G is semi-simple means that G is semi-simple. This definition is not definition. Then G is compact. So the main statement here is that if a Lie group is compact and semi-simple, compact groups usually are semi-simple, but still there is such a thing as a torus, a story, which is not semi-simple. If I say simple, then simply I need to exclude the circle. All other simple, real simple Lie groups are, all other real compact Lie groups are semi-simple. No, what I want to say that compact Lie groups are not semi-simple if they are sums of tori and other. So if I can say reductive, meaning that I allow a semi-simple Lie group plus a torus. Then all compact Lie groups are semi-simple. But I do not state this now. I state only this. This is one. And this is two. A compact Lie algebra is always a Lie algebra of some compact Lie group. So if G is compact, then there exists a compact Lie group such that G is Lie G. This is all not very hard. These two statements are not very hard. The first. I need some geometry, some sort of analysis, at least that you believe. Suppose that G is compact Lie group. G is a compact Lie group. Then we can take the tangent space as the identity, and then we define some Euclidean structure in it. Take some symmetric bilinear form. But I want this form is invariant and invariant. So what do I mean? That if you take some element G and G, then there is the conjugation operation. How not gamma G maybe, which takes H into G inverse HG. This transformation takes DG into itself. This is a representation of this group in this space. And I want that my form is invariant. That is, if I apply, that means that any transformation from this representation is orthogonal, preserves. How to do this? First of all, if I just take some form, then certainly no hope that it will satisfy this property. How to make it invariant? How to make it invariant? You know.
I can guess. You do like an averaging trick.
Yes. There is such a very universal operation, not only in this area. Take the average. So we apply for, we take this form. What's my form? Phi, my form. And I apply gamma G to it. It will be a different form. For every G, I have a bilinear form. But the group is compact. So this form is labeled by an element of this compact group. And I take the integral of over G. If you wish, you can divide it by volume of G to make it real life average. This integral certainly requires the existence of some measure, and it is not hard, but still we have now done it here. If you wish, for every yes, we can for every topological group there is such a measure. It is defined called Haar measure. For Lie groups, it is very simple. And if you do this, you have a new form. Also, well, phi was positive. I didn't say this. Euclidean structure. I said this. Now, if you integrate a positive form, you will get a positive form. Just some positive forms. Yes. So this is a positive form, but this is definitely invariant. So in the compact case, there exists an invariant in the product in TEG. Now, this means that the representation ed, so ed becomes a map, a homomorphism of G into S, if it is connected, SO, and here I need to write dimension of G, right? So every element of G gives rise to an orthogonal transformation. This is the differential of this representation. It maps G into SO DMG. But what is this? It is the Lie algebra. But what is this? Well, you know that the Lie algebra of the orthogonal group is the Lie algebra of skew-symmetric forms. If you matrices, if you choose an arbitrary orthogonal basis in your space, then with respect to this basis, elements of this Lie algebra will be skew-symmetric matrices. Yes. So for every Xi in G, this is skew-symmetric. Add Xi as a matrix with respect to any orthogonal basis in this this space in G. Skew-symmetric. And then certainly, if we take the trace, if we take at Xi at Xi. So this is the trace of at Xi squared. This will be less than or equal to 0. You understand? This is the sum of Aij, Aj for all I and j. These are the same numbers with different signs. This is negative squared, which is non-negative. It is 0 only if this happens to be 0, but still we need to consider this case. So this shows that yes, the killing form of the Lie algebra of a compact Lie group is non-positive, but it has to be positive, it has to be negative, if we additionally know that this form is non-degenerate. And if the Lie algebra is skew-symmetric, or if the Lie algebra is semi-simple, then yes. So the theorem number 1 has been proven. Now number 2. Where is this? Well, I will formulate it. So every compact Lie algebra is a Lie algebra of some compact Lie group. Good. I consider a skew-symmetric. I consider a semi-simple Lie algebra, a compact Lie algebra. So G is compact, and again I suppose that we know that there exists some Lie group. G says that the G is G. Right? Now, I want to say that if J is compact, so again, I do all the same. I consider the representation G into SO dim G. Why so? This is because the Lie algebra is compact. And hence, actually, this certainly you can say that since we know that G is compact, this must be a map into GL of G, right? But now, the algebra G has a form, killing form, if you wish, and with respect to this killing form, compactness means that this killing form is strictly negative. This means, an immediate computation shows, that actually the map add is a map into skew-symmetric matrices. Just look. We fix some bases in G. E1, E, n, where n is the dimension of G. Orthonormal. Since the killing form is strictly negative, semi-strictly positive, there exists an orthonormal basis. So this is an orthonormal basis. After which, for every Xi in G, the operator add Xi satisfies the following condition, and I write it using Ei and Ej. So add Xi Ei Ej is equal. I change something, but it is precisely the condition minus this. This is precisely the universality, the invariance condition for the killing form. If so, this actually is the Ij matrix entry for this information, right? And this is, so this is Aij, this is Aji, where A's are matrix entries for this information as C with respect to this basis. So what we have is that this is really symmetric. So as soon as we have this, we can say that our map L is a map of G into the Lie algebra homomorphism of skew-symmetric matrices. Of skew-symmetric matrices SO, well, I write N. And this gives rise to a map of G into SON, map between at this moment, if you wish, I can assume that G is simply connected. I can take the universal covering just to have this existence of a homomorphism between groups. Now, this group, if you don't know, is compact. This map may have kernel, but the kernel of this is central. It's central paragraph of G. If you remember the say if you take this, then the kernel is precisely center of G. But if G is, semi-simple, then no center. For the group, there might be a center. Again, discrete, not having 0 dimension. But this is central by definition of this information. So actually we have this kernel is gamma. We have a map of G over gamma, a homomorphism. SON, no kernel, so embedding. And for this group, again, the Lie algebra is the same. This factorization over this discrete subgroup will not change the Lie algebra. So we have a subgroup of this. Certainly at this moment, if you want to do this, you can say, well, virtual subgroup. We don't know that G is compact. You know, something can be done if we are sure that this group is semi-simple. Because it is true for Lie algebras that certainly we have a Lie subalgebra in SON, right? This add monomorphism also. And this Lie subalgebra gives rise to a virtual subgroup of SON. There are theorems which we proved. I don't want to repeat them. Certainly from our theorem it is immediately follows that if G itself may be Lie algebra through a virtual subgroup, then G prime, its commutator subalgebra, will be a Lie algebra of a closed subgroup. It follows from our construction, so I don't want to repeat this. G is semi-simple. G prime is equal to G. So this is true that actually this is an embedding, becomes a subgroup of SON. And since SON is compact, you know, what else to say? Yes. Now we will do something more interesting. Have you ever heard the word complexification? Yes, I pronounced it many times. Then please tell me, suppose you have a complex vector space. Then you can believe that this is a complexification of some real vector space. I know what you're going to say. Take any basis in this complex vector space and take the real linear combinations of the elements of this base. It will be a real subspace for which the whole space is a complexification. But I want to have something not depending on basis. How to describe, if you have a complex vector space, how to find real subspaces for which this is a complexification. How many of them do we have? We have a complex vector space. right? They're of dimension n. There are many, how many, who knows? There are some n-dimensional real subspaces. It is definitely not realistic that our complex vector space, it has the same dimension, but is not necessarily a complexification of this real vector space. How to describe all real subspaces of a complex vector space for which this complex vector space is a complexification?
Is there 2 to the power n subspaces? Is there 2 to the power n subspaces for which you can have the complexification? I mean,
you can say this thing. I don't know whether you probably you have in mind this. You just take a real subspace, and then you want to say that well, basis again basis. Basis in the space is linearly independent also for complex numbers. So no complex linear combination of the elements of the basis is equal to 0. I prefer to say this in a slightly different way. So we have a vector space V. And now, complex vector space. Now I can do the following. I will call this map a complex conjugation. A self-map, which is, how it's called, antilinear. I mean that omega of lambda V is equal to lambda bar omega V. How do they call it? Antilinear, pseudo-linear, quasi-linear. But I mean this. And omega squared is 1. So consider such a map. All such maps. One such map. And I say now that if you have this, then simply take the set of vectors which are fixed by it. You understand? It is and this is, I state this, a real subspace of V, definitely a real subspace of V, which has the same real dimension as the complex dimension of V, and V is a complexification of this. Why so? Immediately clear. Do you understand the statement? It is an exercise for beginners linear algebra. You see, still this is a complex vector space, so there is multiplication by I. This omega, if you forget that this is a complex vector space, squared is 1. This means that the eigenvalues are 1 and -1. And actually this map is diagonalizable. So there are two subspaces. The one is fixed by omega, and the other one is minus fixed. So every vector in this subspace, in the second subspace, is mapped into negative itself by omega. Right? You understand? But moreover, what do you think the multiplication by I performs for these two spaces? Yes, Colin, precisely what you mean. It takes one into another one. If V is fixed by omega, then IV, because of this, is minus fixed by omega, is mapped into. So these two spaces are taken into each other by this multiplication by I, which from the real point of view an automorphism of this space. So these two parts are isomorphic, they have the same size. There is a transformation in a real transformation in V, which actually multiplication by I, very much complex transformation, which switches them. And then it is clear that we can call one of them real part, another one imaginary part, and the whole space V becomes its complexification. Yes. Now let's do more. So who cares about vector spaces? Here in this room, we consider Lie algebras. Suppose that we have a complex Lie algebra, and we want to find a subalgebra in this Lie algebra, for which our complex Lie algebra is a complexification. How to do that? know how to do that, then just any omega will not work. We need also to require that omega is a Lie algebra automorphism. Takes commutator into commutator. So, if we have a complex Lie algebra and want to present it as a real Lie algebra, then what you need to do is simplification of real Lie algebra. You need to look for a transformation in this Lie algebra, which has square 1. But this property, we could not find a right name for it. Maybe an isomorphism. It's right, eh? Yes. And plus, it is a Lie algebra automorphism. As soon as we have this, we present our Lie algebra, our complex Lie algebra, as a complexification of some real Lie algebra. And now theorem. For any semi-simple, complex Lie algebra, you can take simple, there exists some real subalgebra for which it is a complexification and which is compact. So every complex, semi-simple, complex Lie algebra is a complexification of a compact real Lie algebra. Is the statement clear? If the statement is clear, I have 2 more minutes, and it's sufficient probably to explain how this transformation actually acts. All the details we'll present next time. We have a complex Lie algebra G, semi-simple. You can remember that this is H right? Now, in this space, there are vectors E alpha and E negative alpha. Now I want to choose them in a special way. I did it once, but now it is important. You see, there exists an automorphism of the root system, which takes alpha in negative alpha. And this takes E alpha into some number times E negative alpha, because it switches G alpha and G negative alpha. But I want this number to be 1. And it's possible to do, because actually the choice of E alpha in negative alpha was not unique. We can multiply E alpha by the number, and this by the inverse number. And this will be okay. The only requirement was that E alpha is in G alpha, and the commutator of these two is H negative alpha, minus H alpha. This is called Weil basis, and there is, I will repeat this next time, very simple way how to do it. As soon as you have it, every element of G becomes an element of H plus the sum lambda alpha E alpha. I don't like this. I prefer to choose a basis H1 HR basis in H, and then say that every element of G is the sum. It's a complex Lie algebra. All numbers are complex. Mu I HI plus the sum lambda alpha E alpha. And now my last word. My transformation omega, which will be all I need, is the following. This is taken into minus the sum mu I bar HI plus the sum lambda alpha bar E negative alpha. Very explicit formula. And we need to check that it is a Lie algebra homomorphism, and that and also that the Fuchs, the space subalgebra, if Lie algebra homomorphism of the fixed points, its Killing form, just the restriction of Killing form of the whole algebra to this real part is strictly negative. For this, you don't have time today. Thank you.